Programming paradigms are essential to computer science as they outline the way code is styled and written. When I was younger, I thought the object-oriented programming was the only right way to code, and Java was the best language. So obviously, I wasn't the brightest back then. I realized constricting myself to one paradigm wasn't a smart decision, and expanding my options could greatly increase my coding quality. I'm going to mainly focus on the object-oriented and functional paradigms, as OOP is arguably the most used paradigm, and functional programming is also growing rapidly in popularity. While coding, there's multiple ways to solve a problem, making the debate of which paradigm is the best useless. The idea behind object-oriented programming is to rely on the concepts of classes and objects, where a class could be considered a blueprint to instantiate objects. Classes usually represent a broad category such as cars, animals, or any other encompassing field. For example, if we have a class foo with attributes supply and type, we can now create as many objects of food as we like. To add some more functionality, the class food can have methods. Most classes are even more powerful than they look like, as they can be extended from to make more subclasses. Here, KitKat can extend from food. With KitKat, everything is the same except the consume function is overridden. While this specific example is extremely simple, an object-oriented design allows for flexible code reuse. Object-oriented programming can be made more robust with features like abstract classes, interfaces, virtual functions, multiple inheritance, and more, but that's beyond the scope of this video. Something you'll probably hear a lot related to object-oriented programming are its four pillars. These are inheritance, polymorphism, encapsulation, and abstraction. Inheritance is what I mentioned earlier about KitKat extending food. KitKats are still a type of food, so they should be able to take all the properties of food. Encapsulation allows classes to manage how they hide data, allowing access through either the class itself or a function. For example, if we have a class for a person, we wouldn't want their address or SSN to be public. Otherwise, any other class would be able to access and potentially change those properties. On the flip side, something like your name could be public, as that data isn't as sensitive. The best practice is to declare any variables as private, so nothing outside the class can affect it, unless it needs to be public. Abstraction is similar to encapsulation, however, it's less about data safety, but rather for ease of use. If we have a string and we wanted to make it lowercase, we can just call the toLowercase function, as we don't need to know exactly how the string will be made into lowercase. Polymorphism is also similar to inheritance, except it's about modifying behavior rather than taking properties. In my earlier example, polymorphism is used when we override the consume function. Object-oriented programming is not perfect, and it has its issues. First of all, the code made with object-oriented patterns will generally be longer than other styles. There's just more boilerplate code to write, and if the project doesn't need all the boilerplate, there'll be a lot of extra unnecessary code. That's where functional programming can come in. I apologize in advance if I get something wrong with functional programming, as I don't have a great deal of experience in it. That being said, reading and writing well-written functional programs feel great, as they can be extremely elegant. The main idea with functional programming is that we use functions as our primary building block as opposed to classes and objects. The functions are usually pure functions avoiding shared state, mutable data, and side effects. For example, if we have a function that adds two variables and changes a global variable to the sum, this would not be a functional programming concept, as we introduced a side effect. The side effect was caused by altering a piece of data beyond our scope, which is the function. Side effects are something developers avoid as they can cause bugs that are completely unexpected. We can make the function pure by not altering the global variable. Another concept of functional programming is that data is immutable because mutable data can also cause side effects. Instead of having shared state and mutable data, we can alter data by using other functions such as map. All map does is run a function on every element of an iterable. In this case, we just append a fire emoji to the end of each string. Map is also an example of a higher order function, as it's a function that takes another function as a parameter. Functional programming has many benefits that object-oriented programming doesn't have. You can get these beautiful or ugly one-liners depending on how you like your code to look. It's also far easier to track down bugs, as a bug should only be contained within one function and won't have you jumping through 10 different files and nested objects. Although functional programming seems like a developer's dream with smaller projects, it can be considerably harder to scale up in certain cases. This is because modeling a problem with functional programming is not as easy as it is in object-oriented programming. For example, take a car that needs maintenance on a certain date. In this case, we can just have a car object with an attribute for when it needs maintenance. In a functional approach, as there is no state, we would have to use a function to find out if the car needs maintenance. I'm not sure if that's the best way to do it, but if there's other methods, feel free to comment them down below. as I would love to know about them. As you can see, both these paradigms, just like every other paradigm, have their benefits, but also a wide variety of issues. I read something on Stack Overflow along the lines of object orientation can improve with functional programming, and I agree. Not everything has to be the same, however, the functions can improve. Methods can take the principles behind functional programming functions. They don't need to have zero side effects, however, minimizing them would be extremely helpful for debugging. The longer object-oriented code can also be split up into sub-methods to do smaller tasks. And since object orientation allows abstraction and encapsulation, the end user doesn't need to see those changes. Paradigm languages are on the rise and are here to stay.
And then suddenly AI boom started. Everyone was like, okay, now we have to work on AI. And the easiest language to work in AI is startups preferring to work with React, Python, because the problem is when you learn it, you're not implementing it. And if you're not implementing it, it's of no use. Don't you get bored by making the content? I was like, actually I get bored. So I wanted to do something different in Python. So what I did is I used a lot of VFX.
Can you share what point of time you thought of quitting your job?
Because technical skills will take you somewhere, networking skills will take you everywhere.
Quitting your software job to become
videos on those things which he wanted to learn. He wanted to pay me, but then I thought not a good time to pay now, let's say later. But that's how we started. I started uploading videos, 2016 came, and then you mentioned about Kotlin, Google announced.
So hey guys, today we have Suyash and he's having 2.5 years of experience in Java and Spring Boot. So let's get started. Hey, hi Suyash, how are you?
Hello, Faizan. I'm good. What about you?
Yes, I'm also good. Shall we start?
Creating the whole whether it's basically start the application by skipping those test cases.
Okay.
Which is once initialized, we cannot change the state of those objects, those are called as immutable. Let's say we have a string,
Okay.
which is a
So hey guys, today we have Manthan Sharma and he's having 3 years of experience in Java.
I can recall.
So hey guys, today we have Suyash and he's having 2.5 years of experience in Java and Spring Boot. So let's get started. Hey, hi Suyash, how are you?
Hello, Faizan. I'm good. What about you?
Yes, I'm also good. Shall we start?
Yeah, we can. Sure.
Okay. Can you please introduce yourself?
Welcome back to the channel. Today I'm going to talk about full stack developers, one of my favorite topics. And to make it more interesting, we've got special guest today, his posture. So he says, trusty manager, can you get the app built by himself? So why not get half of it? And the response, because infrastructure engineer, let's build a Kubernetes cluster for this app. Why not? 100K. But you're, because the money is being used against him. There's more money to devalue his work. Story. Basically, Thanos snapped people from a dev team out. So remember these guys? Dev guys. I know. Well, maybe next to build the software. Big brain, Galaxy.
Let's talk about how DoorDash switched from a monolith architecture to a microservices-oriented architecture and a lot of the issues that they faced. I think a lot of people, especially beginners, assume that like microservices are like the perfect solution. They're perfectly scalable and they don't come with any side effects, but that's not really the case. Before we get into it, let's first understand why DoorDash would want to switch to microservices in the first place. So to give some context, again, it was in 2020, so at the beginning of the pandemic. You can imagine that DoorDash had a pretty big traffic spike. Just using Google Trends as like a proxy for the traffic, you can see I searched for DoorDash. Necessarily have to do with adding a bunch of servers, but a code base is more scalable as it grows when it's readable, and I think static typing is a way to make code bases more scalable. But another distinction generally is that microservices are owned by separate teams. With the monolith, every developer was working on it. And they might have separated it like this part of the code is belonging to one team and this part of the code belongs to another team. But generally speaking, it's better for a team to own a microservice because it can be deployed independently, among other reasons. So there are valid reasons to switch to microservices. I think in DoorDash's case, it was very valid, but they ran into some very significant issues, and let's get into them. The first failure is called a cascading failure, and conceptually, it's actually pretty simple. It's no different than like dependencies. If you have a dependency that is failing, then your original code is going to fail. This could be an example of a relatively simple microservices architecture. You have a service which calls two other services, and each of those depends on another service, which is the one that is reading and writing from a database. So if at the database layer, for whatever reason, there's higher latency. I think in DoorDash's case, they were doing some database maintenance, and so that increased the latency. From the perspective of Service 4, this was actually acceptable. Just to keep it simple, let's say the latency here was like 1 second or something like that. Suppose Service 3 is making a relatively simple request, and suppose that the latency here is like another 1 second, and suppose that that's acceptable. Like a couple seconds is acceptable, though I'm using like very simplified numbers. Usually you'd want the latency to be smaller than that, especially given that these are services, like these are not clients. Typically in a microservices architecture, you'd want to have instances of your services hosted in the same data center or location. And in that case, like these latency numbers would be very, very small, on the order of milliseconds, like 10 milliseconds or tens of. But from this path, the latency is too high, because imagine from the first service, it's the first one that initiated the call. It's waiting. It waited for service 2 to make the call to service 4. It waited for service 4 to make the call to the database. All that latency is propagated back, and this is a 1 second latency as well. And maybe that's the cutoff where the request will time out. API network requests do have a threshold, unless you're using like streaming or something. But suppose that this was too much latency, and therefore this request didn't just take long, it completely failed outright. That's what a cascading failure is. You have an issue in just one component. It was just the database layer that had the issue, and then that was propagated back. And so it's not as if this can't necessarily happen in a monolith architecture, like an increased latency from the database could time out requests within a monolith architecture as well. But in this case, I think it is more difficult to debug. You'd need some kind of like tracing tool. At Google, we had like plenty of this, because as you can imagine, like Google is all microservices. So there's a lot of good tooling at Google. But imagine from DoorDash's perspective, they're just starting microservices. They're not necessarily experts. And this stuff. I mean, you can read about it on books. You can watch this video right now. You can read a blog post, but until you actually get into it, until you actually start building, you have no idea what's going to go wrong. By the way, I want to quickly mention that a trace tool is basically a tool for like observability. So like kind of the same way you have one service making a request to another, like you have information about that request. You have like the status code, how long it took, like what was the response to it. But imagine you have one request that's making a request, and there's like a bunch of other requests involved in that. That's what trace means. It'll trace that entire request. You can imagine a tool like that makes debugging something like this very trivial, just because like you would see the latency. You'd see the latency at every single step, and you'd see, okay, well, the database layer is the one that's responsible. Imagine that there's 10 different services involved in a single API. call. Going to be pretty hard to debug that without a tool like this. Probably the better word to describe it, if you want to like Google it, it's called distributed tracing. The second failure type was retry storms. So let's add some context. Imagine you have a healthy system. One service calls another, and then there's a response. It's good, latency is good, there's no error. Maybe once in a while there's a transient error. Maybe for whatever reason the latency was too high. Usually it's latency related, but there might be some like random error. If the request is failing a very small percentage of the time, an easy way to fix that is to implement within the application code some retry logic, right? Just retry the request maybe once or twice or a certain number of times. Very good intentions, because most of the time it will mitigate the issue. But imagine that a service is overloaded. Too many requests are being sent. So this service is going to respond with a failure. It doesn't have the capacity to process the request. So if there's some retry logic built in here now, what's going to happen? Well, it's going to retry. Suppose we code this to retry like 3 times or 5 times, whatever. There's a limit to it. It's not going to retry forever, probably. But even with that, so now imagine like there's 100 queries per second happening here. Let's say the retry logic was like retry 5 times. This service now is going to, instead of normally like in the healthy system, it would send 100 queries per second here. But now in the failing system, it's going to keep retrying. It's going to retry 5 times, and all 5 of those are going to fail. So this is going to be 500 queries per second. So unintentionally, we've taken a service that has too much load, and unintentionally, we increased the load by 5 times. Not good. By doing this, we're pretty much further exacerbating the issue. We're making it worse. Now, there are some ways that DoorDash mitigated this. Try to guess what they are. The first one that came to my mind, honestly, was just like exponential backoff. That's kind of like the first layer of defense, I think, against this. But I guess in DoorDash's case, that probably wasn't enough, because they actually did not mention this in their blog post at all. They actually had a different solution. Keep watching. Request latency, but what's the latency to spin up a server? For example, with AWS like Lambda, that would be considered the cold start. So services failed, they're being replaced, but they're not quite ready yet. They need to start. There could be a variety of like startup tasks related to just like starting the machine, executing a bunch of things at a stable failure. What does that mean? Well, it's actually simple. Imagine that a failure is caused by some reason, a traffic spike or a service going down or whatever, and then at some point that issue is fixed. For example, the traffic spike went back down, but the failure now in the system still exists. Basically, it's like a negative feedback loop that imagine you have a service that talks to another and it makes different kinds of calls. This is going to be a pretty oversimplified example, but imagine one of the types of calls is related to payments, and perhaps another call is related to fetching images. I don't necessarily know that like the same service would be responsible for these, but again, this is just an example. Imagine that this service is experiencing an increased load. It can't keep up with all of these requests. What do you think a solution would be in this case? Thinking about the user experience, payments is pretty important. You don't want that to fail, and that's kind of the bottom line of a business. In DoorDash's case, maybe the images of the food that's not a deal breaker. The app can technically still function if we're not fetching images. So an intelligent decision would be to do something called load shedding. This service will say, sorry, I'm not going to fulfill these requests right now. It's been programmed to do this. And how do you think it's going to do it? How do you think it's going to know it should drop certain requests? It should be programmed, obviously, to have some kind of ranking or precedence, like these are more important than these, sure. But what is it going to monitor? Probably its own resources. That's the simple way. Like, that's the local way to implement this. That gives us a local view of the system. This service is responsible for itself. But there is actually a way to implement this globally, which DoorDash is getting into, but you can read the full article if you want. Details on that. But so based on perhaps like CPU utilization, something like that, it will choose to drop certain requests. That's load shedding. Another countermeasure DoorDash took was something called circuit breakers. It's kind of the inverse of load shedding. Similar example, you can imagine like the payments and images example, but from the perspective of this service, it's going to say, well, okay, I have two types of requests. I'm getting an error from the downstream service. It's returning an error to me. So based on that metric, I'm going to stop certain requests, probably the less important ones. And so this is another version of a local countermeasure, because notice from the perspective of this service, it's only monitoring what it can see. It's getting errors from the downstream service, so it's going to then make the adjustment. But couldn't you imagine perhaps a better solution? I mean, this guy could have more information about the entire system. It might directly know the CPU utilization of the downstream service. Now, this is more difficult to orchestrate because you have a very big system. There's a lot to do, but it's definitely worth exploring. And that's exactly what DoorDash did. But again, we're not going to cover it in this video because it's more complicated. The final countermeasure that DoorDash mentioned was auto scaling. So this is a very obvious solution. As the load increases, just scale up. But the subtle point is that in DoorDash's case, they actually do something called predictive auto scaling rather than reactive auto scaling. Reactive auto scaling is pretty much like the classic AWS Lambda case where like as the load increases, there's going to be more and more instances and it happens automatically. Predictive auto scaling is programming the system such that based on like traffic patterns where for DoorDash, it could be pretty predictable. For example, like during the daytime, you can imagine that services like hosted in a country during the daytime are going to probably have higher load, and during the nighttime, it's going to have lower load. That's an example of predictive auto scaling, and the system, it would tech earlier where if certain nodes get overwhelmed, they're going to try to be replaced or like auto scaled.
Hey guys, today we have Shrikant and he's having total 14 years of experience, 7 years in Oracle and 7 years in Java, Spring Boot and microservices. So hey, hi Shrikant, how are you?
Yeah, hi. I'm fine. How about you?
Yeah, I'm also good. Shall we start?
Yes, please.
Yeah. So
A common database also we have a separate service.
Mhm.
Okay. Now, let us say, since we are using common database,
Good morning.
Yeah, good morning. So what was your name?
Patients. Do well first it will check the content.
One thing that you probably learned from this is that, okay, maybe I have certain ideas that are there and that I like needed a little push in trying to formulate it properly, but then
And I thought that the talent you have is the talent you're born with, and that's all you've got, right? So if as good as you are in high school, that's probably the best you're ever going to be. And boy, that's dumb.
Welcome back to the Free Code Camp podcast. I'm Quincy Larson, teacher and founder of freecodecamp.org. Each week, we're bringing you insight from developers, founders, and ambitious people getting into tech. This week, we're joined by John Washam, who's both.
There's always like the, will I ever be as good as like Linus Torvald?
Programming job, and it's specifically designed for self-taught developers. Lane Wagner has created some.
We're hiring. The people that go to these jobs are hiring managers. We used to.
Really, when you're on the phone with a recruiter, with an HR person, with a hiring manager, they're a person and they have problems. You should be really humble about the process. Right? So, for example, just realize there's a few different types. And this, again, just goes to say, like, you will need to do a lot of interviews because you're going to need practice with each different type of interview. So expect to do, 5 to 10 interviews before you're getting, an offer or two. Now, there's really a few different types of companies that you can apply for, and they all will have very different interview processes. So, for example, if you mostly apply to FANG companies, so Facebook, Apple, Amazon, and then like S is the input, and like that's it, just the signature. And you might ask a follow-up question. We just want a single string in, single string out, right? And what this means is you're just writing a part of the function and you're making sure that you're on the right track. Because the last thing you want to do is get like 10 minutes into solving this thing, only for the interviewer to be sitting there puzzled, like, what are they doing? Like that's not at all what I asked for. So what you kind of want to be doing is prompting for feedback as much as you can as you work through the problem. It's not just good for you because you'll get more hints. It's good for the interviewer because it shows them how you think through this stuff, right? Which is actually more impressive rather than less. So we just want single string in, single string out, right? Interviewer says, yep. And in the interview. So let's do exactly why it's easier to get a job on site.
Master Spring Boot and Spring Security. Master Spring Boot and Spring Security.
So then I'm just going to call it I product. Let me go to this model right here. In this case, so we have category name. So right here we have at items, right? So we'll say private. It's going to increase. So anytime item is cards, right? So here we are getting this card, and the card is actually getting this card item right here, right? Repository, user repository to GTO, and then we're going to pass in. We're going to pass in the user. So let's pass in the user right here. It's a new operation, so we're going to create inside the e-commerce. We're going to create a new folder, and this time around we're going to call this one order. Have users already, so now add 8 watches. So it will be all of these. For example, you can just take merge, or you can just take through uniform version. So let's scroll up right here to the properties. So if we go here, we'll see that we have extracted the properties right here. So these are properties. So here we have the JJWT import.
Hey everyone, welcome back, and let's write a large number. We assign the value to 0 in the Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem word break. So we're given an input string and a dictionary of strings called wordDict, and we want to return true if and only if S can be broken up into separate strings such that every separate string in S is also found inside of our wordDict. And we are allowed to use words from the wordDict multiple times. So for example, let's say we're given an input string leet code, and we're given a word dictionary of words called leet and code. So obviously, in this case, we could split this string, right, into separate strings, leet, right, break it down in this middle position, and then the second string would be code, right? So clearly, this can be broken up into words that are found in the word dictionary, so therefore we are going to return true. Now, what if we took code outside of our word dictionary? Well, then in that case, this portion, leet, is a word, right? But we have no matching word in our dictionary for the remainder code. So in that case, we would have to return false. And, let's say we had an input string instead called leet and leet again, right? So 2 leets in a row, would we return true? Yes, because we're allowed to use this word from our word dictionary multiple times. Right? Clearly it matches this, and it also matches the first portion. Now let's start off with the brute force approach. How would we even structure a brute force solution? Well, there's actually 2 ways to do it, but one of them happens to be more efficient, and I'll tell you why. So one thing we could try for an input string like this one, we could check, okay, the first character, right? Basically the first prefix of this string, L by itself, right? Is this a word that's found in our word dictionary? It's not, right? So let's try maybe the first 2 characters together are a word, right? That's not it either. We would try the first 3, right? Basically, we would try every single portion from the beginning until we found a matching word that does exist in our word dictionary. And we know that we are going to find one like this, right? The first 4 characters of the string are a word, right? So once we found that, what are we going to do? Clearly, we have a sub problem, right? We found a matching word for this portion, but now we want to know, can we break up the rest of this string with words from our dictionary? So that's kind of how we're going to do it, right? That's what's going to be the sub problem, basically. So instead of starting from the first position in the string, we would start at this position in the string and try to word break it. Now, in this approach, what we're going to basically be doing potentially is from every single starting position, right? We're going to check every prefix, right? So from the first starting position, we might also get, if this happened to be a word, then we would start at this position and then do the same thing for this, right? Every word starting here. So basically, we're going to try every word. How many different words are we going to end up trying? We're going to try, let's say n is the size of our string n, and we're going to try basically from every single starting position to the end. So that's going to basically be n times n. Now, we could also do it a different way. Instead of trying every single possible, prefix, let's just check every word in our word dictionary and see if that matches. For example, this first word is 4 characters long, right? So what we're going to do is we're going to check the first 4 characters in our string. Does this match this word? Clearly it does, right? So what does that tell us? That tells us now, we have the same subproblem as before. We're going to start from this next position now, right? And check. And from here, we're basically going to be doing the same thing, right? So we're going to check, is leet basically, the first 4 characters, does that match leet? This does not match leet, right? So now let's check the next word in our word dictionary and check, does that match the characters over here? It does, right? We found code. So this is basically another way to do this problem. Instead of checking every single possible prefix, right, of any length, what we're going to be doing is we're going to be checking every single word in our word dictionary as the prefix. So instead of being O of n times n, we're going to be doing O of n because potentially we are going to be going through every single starting position, but we're going to be multiplying by the number of words in our word dictionary, which is, let's call it m. And the reason why we're going to be doing this approach is because it's going to be a little bit more efficient. And the reason is they tell us below in the problem statement that the max size of word dictionary is going to be smaller than the max size of the string. So this is overall probably going to be more efficient. Now, this isn't going to be the overall time complexity. We are actually going to multiply it by another n, because when we're checking, for example, this string, when we're checking, does that match the first 4 characters here? That's also a n time operation, because it could, potentially be the size of the input string s. So this is basically going to be the overall time complexity, n squared multiplied by m. So I'm just going to basically show you the same formula that I usually do. I'm going to give you a quick illustration of what the decision tree words we're keeping track. We're not going to continue down this path. Now let's try code. Does code match the first 4 characters? Definitely not. So we're not even going to continue down this path either. Of course, neat does match this, so we are going to continue down here. We're going to do 3 more decisions, basically 1 for every single word in our word dictionary. Now, one thing though is when we are starting here, we know we matched the first 4 characters, so by this point we are now going to be at I equals 4, meaning we're going to be looking at this part of the string. So as we can see, checking neat, that's 4 characters long, so let's check 4 characters starting from here. That's not matching, of course, so then we're not going to continue here. Leet, does that match over here? Nope, we're not going to continue down this path. Code, does code match this portion? Yes, it exactly matches. So therefore, we are going to update our I pointer again. Since we matched 4 more characters, we're just going to take I and add 4 to it now. So now I is going to be at 8, and 8 happens to be that exact position right after the end of the string, right? This is where index 8 is. Therefore, we basically know that we were able to match the entire string. Therefore, we know we can return true, right? Once we find a single true, that means we just terminate, we end the function, we can just return true, and the function is done. Now from this example, it might not be super intuitive why we would use a cache, but let's say we had another path in our decision tree that led us to, for example, index. Discovered that our base case 4 characters starting from here, we would go out of bounds of this string, right? There's not enough characters. So of course this is going to be false, right? It wouldn't match equal to position. If we started here, would we be able to match any of the words in our word dictionary? Again, not. So DP of 3, DP of 2, and DP of 1 are going to be false, meaning we cannot word break this string if we start at any of these 3 positions, basically. Now we're finally at the result that we were looking for. DP, we know the length of the word neat is going to be 4, so basically we can replace s plus 1 for our base case, and we are going to initialize our base case. We know that it's the last position, basically the position out of bounds of the string, so the length of s, and we know that's going to be set to true. That's our base case. So now we're going to go through every position I in the length of the string, starting at the last index and working our way to the beginning. So that's why I'm using the decrementer of -1, and we're going to go up until the beginning of the string. And for each position I, we want to try every single word in our word dictionary and see if the word matches this portion. So first, we have to see if starting at position I, the string S even has enough characters for W to be compared to it. So what we're going to do is we're going to check I plus the length of W, and we want to know, is it less than or equal to the length of S? If that's the case, then that means there are enough characters in S for us to compare them. So that's exactly what we're going to do. We're going to, if this is true, then let's compare. So we want to know if that's true, and if S starting at index I, going up until I plus the length of W. So basically, let's say W was 3 characters, then we want to know the first 3 characters in S starting at index I, are they exactly equal? If they are equal, then we want to know, okay, so DP of I is going to be set to DP of I plus the length of W, right? That was the relationship we got, I plus the length of whatever the word happens to be. Now, if we got a single way to word break this starting at index I, that means we can basically stop this loop, right? We don't have to look at every single word in the dictionary. If we found at least one way we were able to word break it, then we're going to stop. So basically, if DP of I is true, then we can break out of this for loop and then move on to the next index. So we're going to start basically at the last index, keep going until we've gotten to index 0, and then once we've done that, we know we can actually return that, and that's going to be stored in DP of 0. So believe it or not, that is the entire code, about 10 lines, I think. And this